welcome to GemChem. Now today's video is on solutions and colligative properties part 4 video, and here we are going to derive the colligative properties. Now here we will deal with relative lowering of vapor pressure and elevation of boiling point using the concepts of chemical potential and thermodynamics. In one particular video we have already dealt with chemical potential, and the knowledge of that one will be used for this, and already 3 videos are uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. Now first we will deal with the relative lowering of vapor pressure. Now for this derivation we need to know the Raoult's law, which has already been discussed in the previous video, right? Now here P1 star minus P1 is taken for the lowering of vapor pressure. Only the difference taken, where P1 is partial vapor pressure of solvent over solution in equilibrium at T Kelvin, where T is one of the temperature which is kept constant, and P1 star is partial vapor pressure of solvent in pure state at T Kelvin. And this difference is written as delta P1. Now this P1 can also be written as X1 P1 star from Raoult's law, and this is applicable for ideal or ideally dilute solution. So now we take the P1 star as common and we get 1 minus X1 P1 star, and we know that the mole fraction of solvent is taken as X1 and mole fraction of solute is taken as X2, and the mole fraction total, that is X1 plus X2, is always equal to 1. So using this concept we can get X1 equals to 1 minus X2, or we can also write X2 equals to 1 minus X1. So from that we have directly written this to this, right? Now ultimately we take this delta P1 divided by the original pressure, that is vapor pressure, partial vapor pressure of solvent in pure state, and this is divided. So we get the relative lowering of vapor pressure, which is equals to X2. And what is X2? It is the mole fraction of solute in solution. And this equation is applicable for ideal and ideally dilute solution. Remember this. And we can also write it like this. That is, if we try to elaborate this one. Here, this X2, if we take the number of parts, then N2, that is for the mole fraction, number of moles of solvent divided by number of moles of solute plus number of moles of solvent, right? So here we can also write in the form of moles, number of moles. Here it is the number of moles of solute, and here it is the number of moles of solvent. And if the solution is very dilute, then the solution is containing only the solvent molecules in excess. So we can also write it as number of moles of solute by number of moles of solvent, and we can ignore the value of N2. Now we will see the elevation of boiling point's derivation. Now at boiling point of solvent in solution at a constant temperature and Tb as the temperature constant, because here elevation will occur in the boiling point and the boiling point is the boiling temperature Tb. We have, by thermodynamic conditions of equilibrium, liquid solvent in solution is in equilibrium with pure vapor of solvent. We assume that the solute is non-volatile, and we have already seen what happens when this equilibrium is established. We can write that the chemical potential of component 1, which is solute, liquid and temperature constant, is equals to mu1 star of pure solvent in the vapor phase Tb. In the video of chemical potential we have already elaborated this part, and this part can be written as mu1 star liquid Tb as temperature plus R Tb ln X1. And what is X1? Mole fraction of solvent in solution. This one is written as it is, that is mu1 star vapor Tb, and always write it as the solution behaves ideally and the vapor behaves ideally. So you have to write it down beside this line that as solution is ideal and vapor behaves ideally. This is important to write beside while deriving. Every point should be clarified, right? Now, after this, we will only take ln x in this left hand side, ln x1, and other terms will be taken that side, mu star, mu1 star v Tb minus mu1 star liquid Tb by R Tb. Now, if you know the equations of thermodynamics, then this is actually delta Vap G star M Tb by R Tb. That is, it is the change in free energy. It is the change in free energy, which can be written like this. That is, the difference between the chemical potentials can be represented by Gibbs free energy change at Tb for pure solvent. It can also be written as Gibbs free energy for vaporization per mole for pure solvent at Tb Kelvin. You have to write these beside delta this part. This part must be defined here, where you have to write delta Vap G star M Tb is what? You have to always mention here. Otherwise, marks will be deducted, right? Now, this equation which we have got previously as equation 1, this one, ln x1. This is our equation 1, and we will differentiate this equation, differentiating this equation with respect to x, differentiating with respect to x. Now what we get is, see here, 1 by x1 equals 1 by r delta Tb delta Vap Gm Tb by Tb, and here we get P, ultimately delta Tb by delta x1 at constant pressure. Okay. Now, if you have seen in thermodynamics chapter the Gibbs-Helmholtz equation, that will be used here. So, by Gibbs-Helmholtz equation, this can be written as like this: 1 by x1 equals 1 by r, and this particular term is being substituted and it is written as delta Vap Hm star Tb by Tb. Here also there must be a star because we are dealing with the pure substance, right? Now it will be like this, and we are left with delta Tb by delta x1. So according to Helmholtz equation, this particular term which we have seen here, this particular term can be substituted by this particular term. Next, molar enthalpy which we are seeing here, delta Vap Hm star Tb. this term is actually dependent on temperature. It depends on the boiling point, depends on TB. So here we can write it like this, that is dTB equals to minus RTB square by delta Vap HM star TB equals into d ln xi. Now what we have done, we have differentiated it. Just we have taken the opposite way round. Okay, previously what was it? It was like this, right? It was like this. We have just rotated it upside down and then we have taken the form of dx1 by x1 is giving us d ln xi. It can give us like this, right? Now if you can see here, what is x1? x1 is n1 by n1 plus n2, right? And this n1 is w1, that is the mass given by the molar mass m1, and this one is w1 by m1 plus w2 by m2. Then if we take all these things down, then 1 plus w2 by m2 into m1 by w1. If we try to write it like this, that is, this can be modified like this, 1 by 1 plus n2, that is this one, this particular thing can be written as n2, divided by w1, which is here, into 1000 into the leftover m1 divided by another 1000, just to neutralize the 1000 which we have multiplied. So ultimately what we get is, now remember this one, n2 by w1 into 1000 gives us the molality of solute in solution. So we can write it like this, x1 equals to 1 by 1 plus m2 into m1 by 1000, and m2 is our molality. Molality, what is molality? We know, right? So molality of solute in solution. Now we have in our equation ln xi, so we can write it as minus ln, we are rotating it upside down, 1 plus m2 m1 by 1000. If we do d ln xi, then it is near about minus 1 by 1 plus m1 m2 by 1000 into m1 by 1000 into dm2. Next what we do is, we directly substitute this value in dTb, which becomes plus RTB squared by delta Vap HM star TB into the total value which we have got now, that is 1 plus m1 small m2 by 1000 into m1 by 1000 into dm2. Now ultimately from here we can understand that we are near about to the lowering of vapor pressure, which can be measured using the difference, right? So this is one kind of difference. So we can write it now. This one will be taken in the left hand side. Delta TB by delta M2 is equal to RTB square by delta VAP HM star TB multiplied by 1 plus M1 M2 by 1000 into M1 by 1000. Now if we take a dilute solution, for dilute solution, remember this M2 tends to 0, and at that condition TB which we have taken is near about the TB star. Now what is TB star? TB star is actually the temperature boiling point in the pure state of the solvent, and this delta H VAP which we have seen here, delta H VAP which was for TB also tends to delta VAP HM for TB star. This is also applicable for TB star. Now we will see our final equation. Now our final equation will be like this: delta TB by delta M2. Here M2 tends to 0, which is near about equal to RTB star square by delta VAP HM star TB star multiplied by M1 by 1000. As we see that M2 is tending to 0, correct? So that's why 1 by 0 is something 1. So we are not taking that term. So this one is totally a constant, and this constant, all are constants, so this is Kb. Properties of pure liquid solvent. You can write it down as all are constant and their properties of pure liquid solvent. So Kb which we have obtained is actually the characteristic property of solvent. Characteristic property of solvent. And it has a particular name, which is ebullioscopic constant. EBULLIO, ebullioscopic constant. It is also known as by other name, that is molar elevation constant. Molar elevation constant, and its unit is like this. If we take all the units of the right hand side, then its unit comes to be as like this. Joule per Kelvin per mole is for the R, Kelvin square for the temperature, and for delta H is joule per mole. For M1 it is kg per mole. So ultimately we get it as Kelvin kilogram per mole. Now from the previous case we have obtained like this, that is dTb by dm2 is equals to Kb. Now if we take this like this, dTb equals to Kb dm2, and try to integrate it from Tb star to Tb, and here from 0 to M2 we will get like this, that is Tb minus Tb star equals to Kb M2, and this is delta Tb equals to KBm2, where delta TB is elevation in boiling point, and we know what is Kb, and m2 is molality. Right. Now this is a derivation where no consideration of solute being non-electrolyte is taken, and if electrolyte taken, then the number of particles must increase and colligative property value will also change. So it is, if we take electrolyte, it is not valid to be applicable for colligative properties. Non-electrolyte has effective molality equals to molality of the solution, whereas for the electrolyte we have effective molality much greater than the molality of the solution. So that's why here we have considered non-electrolyte. And here the topic of elevation of boiling point and relative lowering of vapor pressure ends. In the next video we will deal with depression in fizzing point and also another important topic, that is osmosis, that is osmotic pressure. So hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.